Hello, class. In this lesson, we're going to learn how the Pythagorean theorem is connected to the criterion for perpendicularity. That is, if we have lines with slopes that are negative reciprocals, then they're perpendicular. So to start off, we have a student who believes that a triangle with these side lengths is not a right triangle. Do you agree with her? Yes, no, and why? Well, the student's incorrect, but she has the right idea. She knows that we have to plug into the equation a squared plus b squared equals c squared, because if they satisfy that equation, then it is a right triangle. But we know that c has to be the hypotenuse, and that's the longest side. So unfortunately, she put 5 in for the hypotenuse, and 5 times the square root of 2 is the longest side. So when we do it the correct way, we get 50 equals 50, so it's the right triangle. Same idea here. Would these side lengths give us a right triangle? If so, what would the right angle be? Well, the longest side here is AB. So if it were a right triangle, then the right angle would have to be angle C. It's the angle opposite side AB. But we don't have to worry about that because when we substitute into our equation, we end up with 41 equals 49, which is false. So it's not a right triangle. So now what we want to do is we want to extend this onto the coordinate plane. So let's make this triangle ABO. And do you think it's a right triangle? Well, when we graph it, it certainly seems plausible that it's a right triangle. Looks like angle AOB could be a right angle. But we're not entirely sure of that. We didn't do any rigorous math work to prove that. So what could we do to determine if we do have a right triangle? Well, there's really two main strategies we could use. We could use the converse of Pythagorean theorem, stick with our previous theme, or we could check to see if these slopes are negative reciprocals. And while the second method is entirely valid, to help us with our objective for today, we're going to stick to the first idea. We're going to stick with Pythagorean theorem for right now. So if we're going to use Pythagorean theorem and its converse, what other information do we need in order to solve this problem? We have to substitute in side lengths. And how do we figure out what the lengths of those sides are? We would use the distance formula. Remember, distance and length are synonymous. And so when we substitute, what would the hypotenuse be? It would be AB, because that's the longest side. And so what equation would we write to figure out if we have a right triangle? So I'd like you to think about what equation you would write first without any number substituted in. So name the sides. So if we substitute into a squared plus b squared equals c squared, put the legs over here, and the hypotenuse squared by itself on the right-hand side. And now let's plug in the numbers and see if we do have a right triangle. So we plug in our answers from the distance formula, and we end up with 65 equals 65, so it's a right triangle. So which angle would be the right angle? Well, it would have to be the angle that's centered at the origin, angle AOB. It's opposite hypotenuse AB. And since we have a right angle, what can we say about the legs? How are they related to each other? Well, it's a right angle, so they have to be perpendicular to each other. So similar idea here. I'm going to plot these points, and we want to figure out our segments OP and OQ perpendicular to each other. So when we graph them, we end up with this. And so if they're perpendicular, then this would have to be a right angle. And so it would mean that QP would have to be a hypotenuse. So we can draw that in there. So when we use the distance formula, we end up with these side lengths. So we're going to use QP for the hypotenuse. And in this case, if you had ended up with a hypotenuse that was smaller than one of the other two sides, you know it couldn't be a right angle because you can't have a leg that's longer than a hypotenuse. So PQ or QP is square root of 17, but when we plug into our formula, we would end up, when we simplify, with 10 plus 13, which is 23, and 23 does not equal 17. So it's not a right triangle. So let's extend what we learned to any 2 points that we connect to the origin. So here we have point A with coordinates A1, A2, and point B with coordinates B1, B2. So we know about triangle ABO if these two segments are perpendicular to each other. It would have to be a right triangle, so it has to satisfy Pythagorean theorem. So what expressions can we write that define these three lengths? So OA, OB, and AB. Well, we can use the distance formula to figure out equations for them, or you can use Pythagorean theorem, however you're thinking about it. But you should get these three expressions. Now for AB, it doesn't matter if you wrote A1 minus B1 squared, because we know that if we did get a negative number and we squared it, we would get a non-negative number. So it doesn't matter the order of these two, but you have to have everything substituted correctly into the formula. So if these are perpendicular, then these distances will satisfy Pythagorean theorem. So we're going to work through this one together. So if we plug in to this equation, we end up with this. And what's nice is that the squared and the square roots are going to cancel out here. And let's see, we want to simplify this as much as we possibly can. So we have binomials here that are being squared. So we're going to square each binomial. You know how to do that. And what we notice here, on the left-hand side, we have a1 squared. We have a1 squared over here. They cancel out. We have a2 squared, another a2 squared. You have b2 squared, and the b1 squared. So everything on the left-hand side has canceled out. So we're just looking for the 0 over there. We can simplify this a little bit. If we divide everything by -2, we end up with this equation. So we have shown that if we have points that have an endpoint at the origin, if they're perpendicular, then they must satisfy this equation. So this is a big idea for this lesson. I would definitely have this down in my notebook. So what this formula says is that if we find the product of the x coordinates and add it to the product of the y coordinates, and that must be 0 when the lines are perpendicular, or the segments are perpendicular. So if we go back to our previous example, we knew that we already had a right triangle. And this satisfies the conditions. We have a triangle with one of the vertices at the origin. So we want to make sure that this satisfies our formula that we just figured out. So if we plug in our coordinates, the product of the x's is -12, the product of the y's is +12. So those are opposites and we get 0. So they are perpendicular. This seems a lot easier than figuring out the side lanes and substituting Pythagorean theorem. So this is a nice little easier way to solve that type of problem. So here we have vertices from a triangle that we know is not a right triangle. So hopefully our formula fails here. So the product of the x coordinates is 6. The product of the y coordinates is -3. And that gives us a sum of 3. So that's not equal to 0. So the segments aren't perpendicular. That's what we wanted. And the converse of this also holds. Just like we learned that Pythagorean theorem is true as its converse, the other way around. The same is true here. If we have segments with a common endpoint at the origin and they satisfy this equation, then the segments are perpendicular, and vice versa. So we want to use what we just learned to figure out if we have a rectangle here. So it tells us it's a parallelogram. Now how do we figure out if it's a rectangle? Well, we know it has to have 4 right angles. And it looks like we could use what we just found out about perpendicularity to figure out if we have a right angle here at vertex O. But how does that help us with the other 3 vertices? Well, it's a parallelogram, and we know that in a parallelogram, that opposite angles are congruent. So if this is right angle, then B is a right angle. And consecutive or adjacent angles are supplementary. So if that's 90, and these two add up to 180, then this one must be 90. So all we really need to know is what one angle, if one angle is 90 degrees, then all of them have to be. Right? And that's because we know it's a parallelogram. And if we check with our formula, we end up with -4 plus 4, and that does indeed equal 0. So we have a right angle, and we have a rectangle. So now we want to use everything we've learned today to prove that when we have perpendicular lines that aren't vertical, then the slopes are negative reciprocals. So we have 2 lines, L1 and L2, and the slope of L1 is M1. So the vertical change is M1. Remember, you can always divide your slope by 1, and the horizontal change is just 1. So that corresponds to this, to giving us this point. And the same over here for L2. We have a vertical change of M2. Right? This clearly will be a negative slope, and a horizontal change of 1. So what equation can we write using our previous theorem that we learned? Well, we know that these lines will be perpendicular if and only if the slopes satisfy this equation. So they multiply the x's, multiply the y's, and that sum must be 0. So let's simplify this expression. Or I'm sorry, let's simplify the equation. So simplify the left-hand side expression. And so this is true if and only if 1 plus the product of the slopes is 0. Let's get the m's by themselves. That's true if and only if this is true, right? Subtract 1 from both sides. And let's solve for the first slope. When we solve for the first slope, we see that we have negative quantity 1 over m2. So this proves that these lines are perpendicular if and only if their slopes are negative reciprocals. So in closing, how do we know when two segments are perpendicular, when they share a endpoint at the origin? If their coordinates satisfy this equation. How do we figure out this formula? Well, we looked at a triangle that had a vertex at the origin, we used the distance formula, and the Pythagorean theorem. And what do we know about the slopes of perpendicular lines? We know that their slopes are negative reciprocals, so we proved that in this lesson. In this lesson, we connected the Pythagorean theorem to the criterion for perpendicularity. Thank you for watching this video.